Hey guys, welcome back. We're going to do one last example of re-expressing data. We're going to re-look into the fishing line strength, length versus strength here. So on a standard spool, the higher this test strength for the fishing line, the shorter the overall length of because it'll be thicker, the line will be thicker, so the shorter overall length of line that you can actually fit on a spool. So kind of going into that, explain a little bit there. So it is an inverse relationship to each other, very similar to a reciprocal because they're inverse related to each other. So as one increases, the other one decreases. So as we increase the test strength in pounds for the breaking strength for the larger fish or whatever, the overall length that we're going to have is going to be shorter. It's going to be thicker monofilament line, so it won't actually be as long. All right, so we have our ladder of power here. This looks like a reciprocal, so if I was going to guess, the first one I would do is be the opposite reciprocal, and sure enough, that one actually would work out pretty quick and pretty well. So our one step here is going to be the raw data. That's anything to the power of 1. That's in blue there. We jumped all the way down the ladder to the reciprocal, and we kind of got lucky just from knowing what we know. It worked out pretty well. Could there have been anything that would have worked better? Well, let's try. If we would have squared it, it just actually would have got worse. If we squared it, so that would not have been a good idea. We square them when it looks like a square root curve, when it's curving up, not when it's curving down. It actually would have curved down even further if we would have squared it. That's going the wrong direction on the ladder powers. All right, so if we take the square roots, you'll notice it improves, but only slightly. If we take the logarithm, that's a 0 step here. That one also tended to improve it, but not enough. The reciprocal square root, the opposite reciprocal square root. Remember, we do the opposite so that the signs, the direction stays the same. Otherwise, the association will become positive. That's not what we want. That actually might have been enough, but it's still going to show some curvature left in our residual plot. So let's go all the way to our reciprocal square, or sorry, our opposite reciprocal. And now it looks like it's almost maybe even curving up a little bit, or maybe we haven't got enough. So the next one that we have is from the ladder of powers, is that we could always try the, not from the ladder of powers, from the attack of the logs, which is what we're going to do today, is actually taking the logarithm of both sides. So if I take the logarithm of the x and the logarithm of the y, what it's going to end up doing, which is actually really cool, is it'll fit and it'll find the best or the optimum exponent that you could use instead of using just integers like 2, 1, 1/2, 0, -1, -1/2, etc. It actually finds this this power of -1.08, which is closest to -1. So the model that's the easiest, the best model, of course, would be from the power model, but the one that's the most simple to interpret and simple to use would just be to do the opposite reciprocal. Okay, so it's called someone's razor, I forgot. You can look at the book if you're looking at it, but they explain it really well, and I can't get into all of it, but there's the idea is that we don't want to find the perfect model. No model is perfect. In fact, all models are wrong. Some models are useful. That's from George Box, I believe. And because we know no model will fit the data exactly, there's always going to be error. There's always going to be residuals, but some models are useful if they fit it well enough, and kind of minimize the amount of error. And when we're finding the perfect one, kind of like the Goldilocks, not too big, not too small, something just right, we can always use the power model, and it'll always find the best exponent that we can using. It really uses the power of exponents. You can even read about that if you want there. I'll get into it, but sometimes the simpler model is easier to interpret, even if it has a little bit more error in it, a little bit more residuals, and more variation left unaccounted for. It's still going to be the best model for us to use. So I would stick with the green one instead of this one. So if we go up higher on the model, that's when we take the logarithm of the x, and that is actually the logarithmic model. So if we notice, it's the y hat, it's the logarithmic model, y hat of ax, or a plus b times the log of x. This is when we're dealing with like CEO data. We took the logarithm of the x variable. That's apparently you can also use a logarithmic regression. This option is on the calculator. So let me pull up the calculator real quick, and I'll show you these options because we can do curved models. So if I go to stat, arrow to calculate, instead of linear regression, you could do a quadratic regression, which would be, one of those, like a parabola. Cubic regression, it'll fit with one that's going up and down, which is kind of nice, with to the third power or the order of 3. Quartic, so if it goes up, down, up, down. Linear regression, that's what we use anyway. This is the logarithmic regression, which would do the curvature here that we're talking about. The exponential regression, which we'll talk about that one, and then the power regression, which is the logarithm of both of them. And then you can also do a sinusoidal regression, which will fit a sine wave, which will go up and down just like temperature. So it oscillates up and down, which is kind of cool. And then a manual fit one, whatever, not doing that. Okay, so these options that it gives us, power, the exponential and the logarithmic, that is found by taking the logs of either the x or the y or both. So just the log of the x is the logarithmic regression, which is shown here. The log of the y is the exponential. That's actually this 0 step here, the log of the y. Okay, we use that when we're dealing with percentage gross. And so anyway, you can kind of see how it does it with the x. So it's some base b to the x power, where b is going to be something from your model. And then if we take the log of both, that's a power model. That's what we did here. That's this step here. And this one actually can be located anywhere. It'll tell us the optimum one, the optimum power. And that's actually using properties of logs, which is properties of exponents, which will allow us to find the optimum exponent. But again, we would just pick the integer that's closest to it. That's one of our normal steps. Usually we don't use the power model very often. Sometimes it's the only way that we can actually straighten out some crazy curve data, but not all data can actually be straightened out. So we're just looking for the one. We're just trying to remove as much curvature as we can, and still easy to interpret. Okay, so that's the attack of the logs. So log of the x, log of the y, log of both of them would be your logarithmic, exponential, and your power model. And the log of the x is actually going even higher than squaring. Log of the y, which is your exponential, is the 0 step, and then the power model is, because of the properties of logs, it can be anywhere on the ladder, which is kind of nice. So let's look at the measuring the alligators here. So if I would have started out here, this is already kind of like y is equal to x squared or something like that. It was really x cubed. So if I would have squared it or cubed it, it got even worse. So if I took the logarithm of the x value, notice it gets worse. So using the, I think that was the exponential model, or no, using the logarithmic model, that would have been worse. We even have even more curvature with our residuals that we see back here as well. Okay, so that's not what we want to do. That's going the wrong direction. Taking the square root is improving it, but not enough. What we actually need to do is a cube root, which is y, because we're going from length to volume. That's what we would naturally do. We actually found that taking the logarithm of y would be even better. Even though it doesn't quite make a whole lot of sense, it is a better model. There's no more curvature here like we saw in this one here. We still had that curvature going down and going up, but once we took the logarithm of the y, which would be the exponential model, it got rid of that. So that's our best models that we have so far. And then we could have gone even further to the opposite reciprocal square root, which went too far, and then clearly the opposite reciprocal would go too far as well. And now all of our curvature is going up, which is not what we wanted. So could just do Control Z. So our best model that we should use, and the one that makes the most sense, would be to use just the logarithm of the y, which would be the exponential model. Okay. You could also do the power model. This one I didn't do it, but it would give you some value close to 0, and the easiest one. This pretty much straightened it out as good as we want, so we're fine. All right, so let's revisit the shutter speed versus the f-stop, which is what we do with cameras. So as we increase the shutter speed for like fast action, motion, stuff like that, sort of like long exposures, we have to increase the aperture width, which would give us a larger f-stop or a smaller f-stop. I'm not sure how they actually use the units on there. So let's put this in our calculator and we'll graph out again. So stats, edit. I've got a lot of this stuff already pre-populated, but that's okay. So whenever you put this in the calculator, you'll do it as 1 divided by 1000, and then it'll convert it to a decimal for you. So then we have 1 divided by 500, then we have 1 divided by 250, etc. Okay, and then we'll put our f-stops in for the list 2. And you already kind of see how we're re-expressing it, but that's okay. Let's graph a scatter plot, see what this looks like. So I'm going to turn all my plots off. So that's doing the 4th option. Where'd my calculator go? And then I'm going to turn on one of my plots. I'm going to turn on the first plot, and I'm going to go from list 1 to list 4, or sorry, list 1 to list 2. It's 11 o'clock when I'm filming this, and it's a school night, so I'm trying to get through this quick. Sorry about that. All right, so let's hit zoom 9. I don't like the model showing, but it always does that, and I always forget to turn it off. Okay, boom. So there you go. That's what it looks like. This looks like a square root curve, right? Because it's curving kind of down, however you want to describe that. So if it's a square root, we would undo a square root with a square. And that actually kind of made sense because with the aperture, as we increase the f-stop at the diameter, it's actually opening the area by squaring it. So the kind of relationship, just you're going from 1 dimension to 2 dimensions, so we would square it in order to fix it. Also, when we square things that are bigger, they get even more bigger. So it's going to take this stuff and it's going to push it way up, which is going to straighten it out and actually make it linear. The stuff that's smaller is going to kind of curve back as well. Okay, cool. What do you see? Well, I see that it's not linear and needs to be re-expressed. It also looks similar to y is equal to the square root of x, or the positive square root of x. So thinking about squaring the y value will actually fix that. All right, let's re-express it by taking the response variable and squaring it, as you can imagine. So let's go back into here, do stat, edit. We're going to define list 3. I'm going to go ahead and clear mine out, even though it's the same thing. We're going to define it as list 2 squared. So list 2 squared and hit enter. That's going to be the squared f-stops. Now we're going to graph the scatter plot of that out. So just go from list 1 to our new redefined list 3, which is list 2 squared, and then hit zoom 9. And what do you know? It actually looks linear. It looks like we successfully re-expressed it because there's no more curvature in the data. To check that for sure, we would actually look at the residual plot. So let's do a residual plot. Before we can see the residual plot, we have to run a linear regression so that it calculates and updates the residual list to our new stuff. So let's go to stat, calculate linear regression. I'm going to run a linear regression from list 1 to list 3. I don't think I need to store the regression equation, so that'll save me some time. Then hit calculate. Okay, same thing I got there. And then let's graph the plot for that. I think I actually put the plot for that one under plot 2, just so it'd be easier. So I'm going to go from list 1 to the residual list. Remember, you can get to the residual list by doing second stat to go to list option on the very bottom. There's your residuals. And then zoom 9, boom, there it is. And if you notice here, they definitely spreads out. There's like fan behavior, so our model kind of breaks down as we go out, but it is random spread. I mean, I wouldn't say there's any pattern here, especially when I look at the original one. It looks pretty straightened out. This value is just a little low. That's really the only issue that we have. Yeah, but there really doesn't look to be much curvature, at least compared to what we started out with. So I would say this successfully re-expressed the model. Even though there's some fan behavior, as our model goes higher, it becomes less accurate or less predictable. What's the average standard error, or sorry, the standard deviation of the residuals, the average error for the model? That's going to be this value here. I'm not going to show you how to calculate that. You won't need to know it either, and it gets really kind of complicated. What's the correlation? Correlation almost 1. That's incredible. The reason this is so strong is because we're actually measuring a law of physics. Okay, so it's like gravity. It's being determined by a natural law, and that's why it's almost 1. The only reason it's not 1 itself as a perfect correlation is because we actually have rounding error. You can read about the book as well, but some of these values here are rounded off, and that's why your f-stops are rounded off. That's why you have something like this should be like 22.8 or something. The book will tell you about it. All right, we can account for 99.7% of all variation and the shutter speed based on the f-stops or whatever. Or the f-stops based on shutter speed. All right, the f-stops relate to the diameter of the open shutter. Since the amount of light that enters is determined by the area of the open shutter, it's related to the diameter by squaring. So the square re-expression seems reasonable. Yes, not all re-expressions have such nice explanations, but it's a good idea just to think about them. If we're not satisfied with a re-expression given by the ladder of powers, we can also try the attack of the logs. So we can take the logarithm of list 1 and store it as list 4, and the logarithm of list 2, which is our y list, and store it as list 5. So let's do that real quick. I've actually already done it, but I'll show you how to do it. So edit. For list 4, I'm going to define it and clear this out. I'm going to do the logarithm of list 1. Okay. And then for list 5, I'm going to define it, clear. I'm going to take the logarithm of list 2. All right, good to go. And it's exactly the same. Do I need to do the opposite? No, because I'm doing logs, so it's not a problem. Okay, cool. So We did that. So let's look at the exponential model, which is the log of y versus x. So this is the 0 step on the ladder. So our x list stays the same. Our y list is now the log of list 2, which we said was list 5. So let's try that out. I'm probably not going to do all of these just for the sake of time with you, and we'll just jump straight to the answers. But we're going to go from list 1 to list 5. So second 5 here. Then hit zoom 9. Oh, that's still the residual. Okay, so what I forgot to do is to change which plot was on. So turn plot 1 off, turn plot 2. Oh, I need to turn this one off. Turn that one on. Okay, let's try this again. Zoom 9. Okay, cool. So if we notice here, it got worse, didn't it? Well, if we think of our ladder of powers, we wanted to square it. Let me go back to our ladder of powers here. Do I have a better? Yeah. Okay, so we started out with a raw data, which was like a square root curve, and we wanted to square it to make it better, which would be like the log of x, but instead we went down the step to the log of y, which is like the 0 step. So we're going in the wrong direction. So that's why it looks even worse like a square root curve than we originally started out with. So the original one looks something along the lines of this. Nope, that was a re-express. Looks something along the lines of that. We wanted to re-express it by squaring it. It worked really well when we squared it, which is going up the ladder instead of down the ladder. But whenever we did the 0 step, which is going down the ladder, it looks even worse like a square root curve. And then to find the residuals of that, we just simply need to run a linear regression. So stat, calculate for linear regression. We're going to go from 1 to, I think, 5. Yeah, list 5. I don't need to store the regression, so just enter. There we go. Once we've run a linear regression, you don't have to write this stuff down either because I actually give it to you in the table, so it's not a big deal. Then I want to go to here. I'm going to turn off this plot, go turn this one on, and we're going to do residuals from 1 to the new residuals that we just did, and then we hit zoom 9, and boom, there it is. So not that big of a deal. Notice there's clearly curvature there, so it got worse. All right, what about the logarithmic model? This is going up the ladder. This should actually improve it. Is it better than the squaring? We'll see. So we're going to use list 4 to list 2 because list 4 was the logarithm of the x list 1. So yeah, try that out. I'm not going to go through all the steps just for the sake of time. This one's still going to have curvature in it, as you can see here. The one thing I will say is that whenever we're applying this across the x list, our x list is now list 4. So whenever we put that in the calculator for the x list, you use list 4 instead of list 1. So you use list 4 and then the residuals from our new linear regression. Okay, cool. And then don't worry about standard error because I've got that on the table as well for you already. Power model. This is the log of x and the log of y. What's amazing is it straightens it out the best that it possibly could be. The problem with the power model is going to be, actually, let me show this one real quick. So let me run a linear regression and let's figure out what the optimum power would have been. So linear regression, I'm going to go from list 4 to list 5. And I don't need to store the regression. Okay. So if we look here, whatever's going to be in front of the A, that's going to be, or no, it's going to be whatever's in front of the B. Yeah, so whatever's in front of the B, I believe is going to be what power they're saying that we should have re-expressed it to. So the optimum power would be actually slightly less than squaring the y-axis or taking the square root of the x-axis. I think that's what that's actually telling you there. I'd have to think about it for a little bit. But anyway, it's really close to squaring or doing the square root, which is what we did. So we're just going to stick, for the sake of it being a simpler explanation, we're just going to square the f-stops. And it's not like it was able to remove that much more variation in it anyway. And we have nicely random spread here. We do have fan behavior as it increases as we go, but the reason we have the fan behavior is because of the rounding error in the first place. All right, so here's all the possible models we had. We had the raw data, the y versus the x, the square of the y values, the exponential, which is the 0 step, that made it even worse because it was going down the ladder instead of going up. The logarithmic, which was going up the ladder, which is what we wanted. That was decent, but not as good as our squaring, and squaring was simpler as well. Here's the standard errors in case you're, or standard deviation of the errors in case you're curious. The power model, which will always be the optimum one, it removed the most of the variation, but at that point we're splitting hairs. It did have a smaller standard error, so it would be the most consistent one with the predictions, but it's not as easy to interpret, so we were just going to stick with the square. Okay, so 20 minutes, not too bad. There's one problem, but you got the answers there. So I'm working on, or by this time I might have already had your quizzes graded, so you'll have the quizzes. This Friday I'm going to be sending out well, it's different for every person, but Friday my A students will be taking the practice test. B students will be taking the practice test next Tuesday or something like that. And then we'll be taking the actual test for Unit 2 in person next week. So I'll see you guys then. Let me know if you have any questions. All right, bye.